And now, whoops, we have 3 submissions from Simon. Let's look at them. And then random number generator. This, I don't know what this is. Let's see. All right, I'm fascinated by this. What is going on here, Simon? Temp error. Pitch, got pitch. Is it generating a random number based on the audio that's coming in? Oh, there's 4 submissions. So I don't know. Simon, I'd love to hear more about this random number generator.
So this is a thing that generates random numbers from like this. So here,
you made a random number generator.
So this is what I'm gonna do. So what I did is I have my computer and it's hooked up to a microphone. I don't know. This is the worst drawing of a microphone ever. I don't know if that looks like a microphone. And a speaker. That looks more like a speaker. There you go. So there is a microphone and there is a speaker. What the computer is going to do is it's going to send a frequency of A440, so 440, the note A, 440 hertz, and it's going to get played out through the speaker. Then it's going to travel over the air to the microphone. And the microphone will pick it up. But it won't exactly actually pick up A440, right? It has some imperfections in it, so this will only be approximately A440. And then this gets sent back to the computer. So the computer has this generator that spits out a tone of generates the tone of A440. And then there's another part of the computer that analyzes that frequency. So this uses the machine learning model CLIP, I don't know as I like to call it, to analyze that frequency.
Crêpe? Like pancake in French?
I don't know. So this is already going to be not really perfect, and then this is going to go over the wire, but then this frequency will also not quite be, this will not analyze the correct frequency that's going into the microphone, because this is a machine learning model. It's trained on examples to do what it's supposed to do, so it's not actually going to detect the right frequency. It's going to get it slightly wrong, and the microphone also, the picked up frequency is going to be slightly off. So both of these factors are going to contribute to the error of the frequency. So this is going to take 1 second. This whole process. So this is going to play the note for 1 second. And then the computer over here, it will calculate an average. So it will calculate an average. So it will sort of calculate the frequency along some checkpoints, or rather the machine learning model actually just detects the frequency sometimes, but in others, and not others. So it calculates this average, and once it calculated the average, it's going to do this to it. So we take the average that's built, and we subtract 440 to get the error. And then it's going to take the absolute value of that to sort of get the positive error. But then what I do is just multiply that by 100 to get the error in centihertz. And that error will actually be quite random. Not quite random. Basically, this is true randomness. This is randomness from the noise in the air. It's not some sort of pseudo-random number generation algorithm. This is true randomness. Okay, let's try it. Let's play the pitch. All right, 76. Let's play the pitch again. And again. And again. Okay, we got a way off pitch. What is this? Well, I actually talked a little bit in that 1 second pulse, and that messed up that. So where has this gone wrong? Why has it gone so big? The answer is it's gone wrong over here. It's gone wrong over here because I was talking something. I was talking something into the microphone over here.
Here's the microphone.
I was talking something into the microphone, so now there's not just the note that's coming out from the speaker over there.
Here's the speaker.
It was also me talking going into the microphone, and so ended up with why is this note not so close with A440, and it just spit out a really high error. Let's just play the pitch again to see if anything has really gone wrong. And you can see now I got a much more reasonable one. I remember one time actually getting 2 centihertz of error. That's very little. Sometimes you get 10. Typically it's between 30 and 60 or 70. But
why are you calling this true randomness if it's within certain limits?
what do you mean by within certain limits?
Well, the error cannot be that big. Every time it's only this much bigger than the actual frequency you turn on. Or the much smaller.
But those bounds aren't defined, so this makes it. Yeah, but there is this. You can pick, and there's a function in P5 to do this. Just a random Gaussian number on a Gaussian distribution, and you don't actually give it the bound. You give it the mean and the standard deviation, and then you actually get the numbers without bound. You pick numbers more often at the mean, but you're very unlikely, but it could happen that you could pick a number very far off from the mean. So it's not actually so random numbers don't actually have to be bounded. That's something.
But they are bounded in your case.
Well, not really. There is a really unlikely scenario that the error will be quite big, or a really unlikely scenario that the error will be quite small. So.
And if you're like talking, just what happened now, is it still random?
When I'm talking.
You're sort of influencing it though.
I'm sort of influencing it, and I think it actually only becomes more random with me talking, because then when I'm talking, all sorts of different frequencies coming out, not just this pure sine wave. So it even becomes even more random when I do that. And yeah, that's my random number generator. I'm gonna add a few more things, like sort of an adjustment for the frequency and the time and the amplitude and that kind of stuff that the computer's generating over here. And also I'm going to add a slider just to control how big the numbers are. So that's something that I'm going to add. And I'm going to time slider. Equals create slider. Let's go from 0.25 seconds to 4 seconds. The starting value of 1 second. Amplitude slider. That's easy. I'm going to create a slider that goes from, let's say, 0.25 to 1, with the starting value of 0.5. Freak slider. Equals create slider. Point. Actually, no point. No point in putting the point. Let's say 110. to wait, what is this? Goes from 1 hertz. I guess it's pointless. Let's try like 100 hertz just to 20,000 hertz. So let's just put that in 20,000, which is with a starting value of 440. This is a logarithmic slider, so what I really do is I want to try 100 hertz, you know, that's sort of like, but what I really want to do is I want to take the logarithm of 100 and take the logarithm of 20,000 and the logarithm of 440. And what does the logarithm do again? I think what the logarithm does is logarithm base E. Logarithm natural log. So, I'm gonna have to raise it to the power of Euler's number, which I don't actually have natively, but I could use this exponentiation function, so exp. Or I could just use math dot Euler's number, but I think what I can do is I can just say, oh, and by the way, I forgot the factor slider. Factor slider equals create slider. I also want this one to be logarithmic, so I'm going to say hang on, factor slider, I want between let's say the logarithm of 10 and the logarithm of 10,000, starting with the logarithm of 100. What I'm now going to do is I'm going to say amplitude of the amplitude slider value. And I'm going to say here the frequency slider value. I'm going to say here the, oh, by the way, I have to say exponential to nothing. And over here I'm going to say time slider not value. And where do I need the factor slider? I think I'm going to need it here. So I'm going to say times not 100, but exponent of factor slider dot value. So I think now this will do what I want. Logarithm of 440. Exponent of freak slider dot value. It's 271 point. Let's look up what the logarithm function does. Log what does this do? Calculates the natural log of the base E logarithm. And let's look at EXP. E to the power of... Huh. So we're missing something. Oh, I forgot the steps probably. I forgot to say that I want this to range in... Wait, what is the logarithm of 440? Natural log of 440. 6.086. And let's try 9.903. So I get... Actually, actually a very small number out of there. So I think what I have to do is map it or something. Take a very big number in and get a very small number out. So what I can do is I can say time slider. I'm going to say steps of 0.01. Oh, sorry, 0.05. Amplitude slider in steps of 0.05. Frequency slider, oh, that's an interesting one. So over here, what's the logarithm? 9.903. I'm actually going to say 0.05. I don't know if that's going to be quite a good decision. In fact, what I'm going to do, no, this is what I'm going to do. I'm going to say the logarithm of 10. That way, it's going to be as if it's in steps of 10. But, oh no, because the logarithm is scale. It's the logarithm of 10. Yes, it's 2, so I don't want that. I think what I want to do is just say 0.05. 0.05. And over here, I'm also going to say 0.05. Factor slider. I think this is good. The log of 10. Well, what's the log of 10,000? I think, well, let's keep it this way. I was a little bit over. I don't know. These sliders were really a bad idea. These logarithmic sliders. In fact, let's just take out of the sliders. I don't want. So you have like, that was a really good. I had this really good idea. Then I was like, oh, why on earth have I came up with this? Anyway, let's just back up. I can get rid of this console log. I think I know what might have happened. It was the time slider's fault. The time slider is in seconds, and I treated it as in milliseconds.
So maybe you should put it back in?
I'm no, it's too late. I'm just gonna. Yeah, there you go. That's good. Now, the next step is to submit all of these to the community contributions on the codingtrain.com. I'm going to create a pull request.